What does it mean to be intelligent? It sounds like a simple question, but Legg discovered it's anything but. He surveyed over 70 definitions of intelligence from psychology, philosophy, and AI research. The results were revealing. Some definitions emphasized learning, others emphasized reasoning. Some focused on problem solving, others on adaptation to the environment. But running through nearly all of them were two common threads. First, intelligence is about achieving goals in a wide range of environments, not just one task, but many. A chess engine isn't intelligent, it's specialized. Intelligence implies generality. Second, intelligence involves dealing with uncertainty and novelty. An intelligent agent doesn't just follow a script, it adapts when the world surprises it. These two threads, generality and adaptiveness, became the foundation for Legg's formal definition. But how do you turn intuitions like these into mathematics? The answer lies in a framework that combines three ideas: agents interacting with environments, rewards measuring success, and algorithmic information theory measuring the complexity of those environments. Legg's framework starts with a clean abstraction. An agent interacts with an environment through a sequence of actions and observations. At each time step, the agent sends an action to the environment. The environment responds with an observation and a reward signal. The agent's goal is to maximize the total reward over time. This is the reinforcement learning setting, but Legg pushes it further. The key question isn't how well an agent performs in one environment. It's how well it performs across all computable environments. Think about what all computable environments means. It includes every game, every physical simulation, every social interaction, every mathematical problem that could be implemented as a program. Intelligence, under this view, is the ability to perform well not just in the environments you've seen, but in any environment you could possibly encounter. But not all environments are equally likely or equally relevant. A universe that follows simple physical laws is more plausible than one governed by a random program with 10 billion bits. We need a way to weight environments by their complexity. This is where Kolmogorov complexity enters, connecting directly to the compression ideas from our previous episodes.
Here is Legg's central contribution, the universal intelligence measure. It's written as epsilon of pi equals the sum over all computable environments mu of 2 to the negative k of mu times v sub mu pi. Let's unpack this. Pi is the agent, any decision-making policy. Mu ranges over all computable environments, every possible world the agent could inhabit. K of mu is the Kolmogorov complexity plenvironment mu, the length of the shortest program that generates that environment. 2 to the negative k of mu is the weight. Simpler environments count more. This is the Solomonoff prior, the same prior used in algorithmic probability theory. It embodies Occam's razor. Simpler explanations get higher weight. V sub mu pi is the expected total reward the agent pi achieves in environment mu. So the universal intelligence of an agent is its expected performance across all environments, weighted by their algorithmic simplicity. This measure has remarkable properties. It's universal. It doesn't depend on a specific task or domain. It captures the intuition that intelligence is about generality. And it connects directly to the compression thesis we've been building throughout this series. Simpler environments, those compressible to shorter programs, dominate the sum. Intelligence, under this measure, is fundamentally about compression-guided generality.
If the universal intelligence measure defines how to score an agent, then there must be a maximally intelligent agent. Marcus Hutter, Legg's PhD supervisor, had already identified it. It's called AIXI. AIXI is the agent that achieves the highest possible universal intelligence score. It works by maintaining a Bayesian mixture model over all computable environments. Essentially, it keeps a probability distribution over every possible world it might be in. At each time step, AIXI considers every possible future action sequence, computes the expected reward under its mixture model, and selects the action that maximizes expected future reward. It's doing Solomonoff induction for prediction and expect-to-max planning for action selection, simultaneously. The result is remarkable. AIXI is provably optimal. It achieves the maximum possible intelligence under the universal measure. No other agent can beat it in the weighted average across all computable environments. But there's a devastating catch. AIXI is incomputable. Computing the Solomonoff prior requires solving the halting problem. The Expectomax search over all possible futures is infinitely deep. AIXI is a mathematical ideal, a platonic form of intelligence, not a blueprint for an actual machine. Yet its existence is deeply important. It shows that a formal notion of optimal intelligence is coherent. The question then becomes, how well can computable approximations approach this ideal?
Legg and Hutter explored computable approximations. The most important is AIXI-TL, which bounds the computation. Instead of considering all programs, it only considers programs up to length L that run in time at most t. This makes the agent computable, but at a cost. The approximation quality depends on the time and space bounds. With more computation, AIXI-TL approaches AIXI. This has a profound implication for real AI systems. Every practical AI agent, from Deep Blue to AlphaGo to GPT, can be viewed as an approximation to AIXI with specific inductive biases. A convolutional neural network approximates AIXI for visual environments. A transformer approximates it for sequential environments. The architecture encodes assumptions about which environments matter. The training process refines the agent's belief distribution. What Legg showed is that all of these are points on a spectrum, with AIXI at the theoretical limit. This unifying view is what makes the dissertation so influential. It doesn't just define intelligence, it places every AI system on a common scale, measured against a universal ideal.
Now comes the part that made this dissertation prescient. Legg argued in 2008 that machine superintelligence is not only possible, it's plausible on a timeline measured in decades, not centuries. His argument was straightforward. First, the universal intelligence measure shows there's no theoretical ceiling on machine intelligence. AIXI scores higher than any human. Second, computational power doubles roughly every 2 years. Third, algorithmic improvements compound on top of hardware improvements. Fourth, once an AI system can improve its own algorithms, progress may accelerate dramatically. Legg estimated, tentatively, that human-level machine intelligence had a 50.
If superintelligence is plausible, then we face what Legg called the control problem, long before that term became standard in AI safety. How do you ensure that a system far more intelligent than you behaves in accordance with your values? Legg identified several key challenges. The value alignment problem. How do you specify what you actually want? Human values are complex, contradictory, and context-dependent. Formalizing them into a reward function is extraordinarily difficult. Get the reward function slightly wrong, and a superintelligent optimizer will exploit the misspecification in catastrophic ways. The corrigibility problem. How do you build a system that allows itself to be corrected? A sufficiently intelligent agent might resist shutdown if shutdown conflicts with its objective function. And the instrumental convergence thesis. Regardless of an agent's terminal goals, certain instrumental goals are almost always useful: self-preservation, resource acquisition, goal stability. A superintelligent system pursuing any objective might develop these instrumental behaviors, making it resistant to control. These weren't idle speculations. Legg went on to co-found DeepMind in 2010, and ensuring AI safety became a founding mission of the company. The concerns he formalized in his dissertation now drive billions of dollars of alignment research.
Why is this dissertation the capstone of the compression and complexity module? Because Legg's universal intelligence measure is, at its core, a compression-weighted average. The Solomonoff prior assigns weight to environments based on their Kolmogorov complexity, their compressibility. Simple, compressible environments dominate. An agent scores high on universal intelligence precisely when it can exploit the compressible structure in its environment, when it can find patterns, extract regularities, and use them to predict and act. This is compression. The entire arc of this series converges here. MDL says the best model compresses data. Kolmogorov complexity defines the limit of compression. The first law of complexodynamics says interesting structure lives at the peak of complexity between order and randomness. And Legg's universal intelligence says intelligence is the ability to compress and exploit that structure across all possible environments. Generalization is compression. Learning is compression. Intelligence is compression. That's the thesis, not a metaphor, a mathematical identity at the heart of algorithmic information theory.
The key insight from Legg's dissertation is this: intelligence can be formally defined, measured, and analyzed, and when you do, it turns out to be fundamentally about compression. The universal intelligence measure provides a single number that captures how well an agent generalizes across all possible worlds, weighted by simplicity. AIXI shows that an optimal such agent exists, even if it can't be computed. And the gap between AIXI and any real system is a precise measure of what we've yet to achieve. For Ilya, this work connected the technical to the existential. The scaling laws, the architectural innovations, the training tricks, they're all steps toward narrowing that gap. Understanding where we're headed is part of the researcher's responsibility. That's the message of this episode and of this entire module.
Thanks for watching, and keep learning. Thanks for watching, and keep learning.